In section 5.2, we're going to talk about inverse variation functions. Those are going to be equations defined by y equals k over x to the n, where k is a positive integer called the constant of proportionality or the constant of variation. And we'll talk about the properties of those kind of graphs. Now, if the word variation might trigger some memories from chapter 4, when in chapter 4, we talked about direct variation. And direct variation were equations of the form y equals k times x to the n. K times x to the n is the direct variation situation. And if you see k divided by x to the n, that's the inverse variation situation. So there's a lot of commonality between our direct and inverse variation, especially in terms of determining the constant of proportionality. The k is called the same thing in both cases, but we'll have a product in the direct case and a quotient division in the inverse case. All right, let's look at our first example. We have the loudness or intensity of sound, I, and the distance d are related by this formula, where in this situation, talking about an iPod, the intensity of the iPod is given by the formula I equals 64 over d squared. So the intensity is inversely related to the square of the distance. All right. So first of all, we want to fill in our table. So we're going to plug each of these values in for d squared. So I went ahead and already set that up in decimal. So I'm going to pull it over so we can see and write down these values. I've got my I of d. I wrote it in function notation just because it makes it easier for me to autofill my table. And then I can fill in the values here for our intensity, our loudness. All right, so for 0.1, we've got 6,400. For 0.5, we've got 256. For 1, we've got 64, then 2, 16, 5, 2.56, then 0.64, and 0.16, and 0.071. All right, so those are the different intensities depending on how far away you are from the iPod. What's the practical domain? Okay, so my distances, my inputs right here. I have a very small input at the moment of 0.1. So if you're thinking about this, this is meters. So 0.1 meters, that's still 100 centimeters. So if you're imagining holding an iPod 100 centimeters away from your head, you can get it closer to your head if you wanted to like hold the iPod up to your ear or something. So we can get this to be smaller than 0.1 meters, or this is 100 centimeters just for reference, right? That's 100 centimeters, which we can probably visualize as a distance easier than we can visualize 0.1 meters. 100 centimeters. So I could get it to 0.01 maybe, or even 0.001. I can get it real close to my ear. I can't stick it inside my brain, like in my eardrum. I have to get it, it's going to be a little distance away from my ear. So that means that 0 itself cannot be plugged in, but I can get darn close. So we're going to parenthesize a 0 to signify that we can get darn close. Okay, so we're going to go from 0 up till, okay, so right here I'm 30 meters away from my iPod, and the intensity is pretty small. It's 0.071. I probably can't hear it anymore. If it gets much further away from this, the intensity is gonna be so small that I won't be able to hear it. If you get 30 meters from an iPod, probably not really hearing it, maybe just as like a tiny humming. But we plug 30 into our function. There's still some sound registering. Maybe we could go just a teeny bit further. Let's just guess that maybe we can go up to 40, say. But after that, we're going to say, you know what, it's probably just can't hear anything. So guessing that value based on the fact that this one right here is already quite small is going to get smaller and smaller and smaller the larger the value is. So we'll go a little past perhaps as a guess, but certainly not too far. Okay, so mismatched symbols, I'm going to include the endpoint because I can actually plug 40 into the function. I am not going to plug in the 0, first of all, because 0 cannot be plugged into the function. Also, it's not going to make sense in terms of the practical context. Okay, sketch a graph that shows the picture over the appropriate scale. Okay, so when I graph this on decimals, I can see that the graph looks different than the graphs had in the previous section. That's because of the d squared. So in the previous section, my denominator had a variable, but it wasn't squared. And so I would have seen something in quadrant 1 and quadrant 3. Now I'm in quadrants 1 and 2. Now, the quadrant 2 stuff is not going to make sense in context because that has negative input, a negative distance from your iPod. It doesn't make sense in context. So we're going to focus on this other side here. I'm going to zoom over on the data. Whoa, that makes it look a lot worse, actually, because the difference between the 6,400 and the 0.7 height-wise is huge. So I'm zooming back home. I don't like that zoom out. So I'm just going to draw it like this window. And I want to focus on the portion of the graph that is in quadrant 1, but I'll just kind of make ourselves a note that there is a second portion in quadrant 2, but it's not going to make sense in terms of the context. So in terms of quadrant 1, we're seeing this shape, and that's the part that we really want to look at for the situation. Then I'll just make a quick note that there is another side of it over here. Not focusing on that side. So I didn't center this up. I wanted to emphasize that this is the part that we're going to be thinking about in terms of the practical context for the situation. Okay, so as I move closer to the iPod, when I get closer to the iPod, this is happening, right? I'm getting closer to the iPod. So what's happening to the values, the output values? The output values get larger, right? So the intensity gets larger. Or intensity increases. Then they say if you move away from the iPod, what happens? So if I move away from the iPod, I'm in this section of the graph. If I move away from the iPod, I'm going to say that the intensity approaches 0, gets close to 0. I don't want to just say decreases because this increase right here, it's increasing without bound. It's going to 6,400, then it's going to go to 10,000 or 20,000. It's going to get larger and larger the closer that your iPod gets to 0 distance from your ear. It's going to increase without bound. But this is not going to decrease without bound. It's not decreasing down into the negatives or anything. It's decreasing towards 0 specifically. So we have to be specific in what we say. So the intensity, the intensity decreases towards 0. Okay, and the function I equals 64 over d squared belongs to the family of functions y equals k over x squared, where k is just some non-zero constant. And so they are going to have us explore that, having the squared portion of the denominator and what that means for our shape. So we're going to look at the two examples, 1 over x squared and 10 over x squared, and explore those. All right, so I've got my functions, f and g, 1 over x squared and 10 over x squared, and we can see our table here. And we can see the graphs of the two functions over here. They look very similar. I'm going to turn the dots off. I don't like to see those big dots in the graph there. We can see that these look very similar to our 64 over d squared. Okay, so also I can note that the innermost function, that is the 1 over x squared graph, and the one that's a little outermost is a 10 over x squared, just like when we saw them with 1 over x and 10 over x. The 10 over x is a little bit taller and a little bit further away from 0 than 1 over x. So you can see that happening again here. So I've got my table completed. You can fill yours in. And I also have my graph sketched here. So you can see that they both pinch towards the x-axis. They both do get to the x-axis. They both do get to the y-axis. I guess I was looking at the y-axis first, then the x-axis down here. And even though it takes a teeny bit longer to pinch in towards the y-axis, it sure does, and so does it take it down here to the x-axis. Explain why no part of the graph is below the x-axis. There's nothing down here. Well, that's because the denominator is squared, right? So if you take 1 over x squared, even if you plug in a negative number, that negative number is going to be squared. It's going to turn into a positive. So it's because all outputs are positive. Due to the square. due to the x squared in the denominator, right? Because we're going to square them. So when you plug in your negative inputs, they came out as positives. When you plug in your positive inputs, they came out as positives. So you see that symmetry of exactly the same thing on both sides of the y-axis there. So what happens to the y values as the x values increase infinitely in the positive or negative direction? So as the x values increase. So as the x values increase in either direction, what happens to the y values? The y values get closer and closer to 0. So y decreases towards 0. And this means that the horizontal asymptote is y equals 0. Then what happens to the y values as the x values get closer to 0? So first of all, they ask us about positive x values getting closer towards 0. And then they ask us about negative x values getting closer towards 0. But the same thing is going to happen on both of those, is that the y values are going to get larger. So the y values increase. Without bound, they get larger. So increase without bounds is a little bit more precise because it tells us that there's no limit to how high they grow. The y values are increasing, they're getting very, very large, and so both of these help us determine on the next page that the vertical asymptote is going to be x equals 0, because as x approaches 0, the y values get super large. Okay. Do the functions have a maximum or minimum function value? They do not. These ones are not solely increasing or decreasing because they change from increasing to decreasing, but there is no minimum or maximum. This side is all increasing, and this side is all decreasing. If there were to be a maximum, it would be some value up here, but there's no value because they never touch. Okay, so no. And then for a given x value, how is the output of g related to the output of f? The output of g is 10 times as large, right? I write times out instead of the x thing there. 10 times as large as the outputs of f. Are the functions continuous? This is an interesting question. They're not actually continuous on the entire set of real numbers because there is a break right here on the y-axis where it jumps. There are two different pieces where they're continuous. So they are not continuous on all numbers. But we do typically say that they are continuous on their domain. So they are continuous on their domain, which is x not equal to 0. So this question has like two answers. They're not continuous over every possible number, specifically 0. They are continuous everywhere else. So if we talk about their continuity, we would usually say they are continuous everywhere except at 0. Describe how they are similar and how they are different. So they have the same shape. Oh, I'm mistaken. I just realized I'm not talking about f and g anymore. I'm talking about 1 over x and 1 over x squared. Okay, so 1 over x was this shape, and 1 over x squared was this shape. Okay, so how are those similar and how are they different? Okay, so they both have, so let's do similar first. They both have a horizontal and vertical asymptotes. So they have horizontal asymptotes at y equals 0, and they have vertical asymptotes at x equals 0. Okay. Other similarities are no x or y intercepts. and the domain of x not equal to 0. Bunch of things that are similar about them. Some of the differences are that 1 over x is in quadrants 1 and 3, while 1 over x squared is in quadrants 1 and 2. That's a difference, right? Quadrant 1, 3, quadrant 1 and 2. Another difference is their ranges. So the range for 1 over x is y not equal to 0, and the range for 1 over x squared is y greater than 0. So there's a difference in their range. Sorry, I screwed this over. In this function, 0 is the only y value not achieved. You achieve the negatives, you achieve the positives, so the only value you're not allowed to have is 0. But in the x squared function, you don't get any of the negatives or 0, so you just strictly have the y's greater than 0. So they have different ranges as well. Okay, I'm sure there are some other things you might be able to think about now how they're similar and how they're different, but that's a bunch. Okay, so I've got another table and another pair of graphs to do here. Let me get those started. All right, so I got my functions entered. I have their graphs up here. You can see them in my book down there below for the table. So what we notice about these two functions is one of them is 10 over x squared, the other one's negative 10 over x squared. So their outputs are the same but opposite sign. I've got the same exact numbers, just with a negative sign in front of them when I have the negative coefficient of 10. And when I see their pictures, the positive graph is in quadrants 1 and 2. The negative graph is down here in quadrants 3 and 4. So I can see I sketched my pictures down here as well, one at a time, for the 10 over x squared and the negative 10 over x squared. Describe how to obtain the graph of h using the graph of g. You would just flip it over the x-axis. So flip or reflect over the x-axis. Okay, and again, my book doesn't slide up that far very well. When I get to the bottom of the page, it's hard to see, but I'm flipping or reflecting over the x-axis to go from the graph of g to the graph of h. All right, now we're going to sketch the graph of 1 over x cubed. Okay, so let's get that thing going here. And they want us to ask, is this similar to the graph of 1 over x or the 1 over x squared? Okay, so 1 over x cubed, being that it's in quadrants 1 and 3, this is going to be similar to the graph of 1 over x. More so than it is similar to the graph of 1 over x squared. So we'll make that note that 1 over x cubed is similar to 1 over x. All right. And then graph 1 over x to the 4th. And is that similar to 1 over x or to 1 over x squared? Okay, well, this is in quadrants 1 and 2. So it's similar to 1 over x squared. So if I graph this one, I can make us that quick note again here that 1 over x to the 4th is similar to 1 over x squared. And also noting about this that I'm not too surprised by that because in the top, the first two have odd denominators, power 1, power 3. And the odd denominators allow negatives to stay negative. So we're going to stay in the negative side when we have negative inputs. And the bottom two have even exponents in the denominators. So when you plug in a negative, it's going to square or turn to the 4th power, and it's going to turn to a positive. So the even powers look similar to each other, and the odd powers look similar to each other. Okay, so onto our inverse variations down here. We've already talked a little bit about the form y equals k over x to the n. That's going to be the formula for inverse variation, where k is the constant of variation, or also called constant of proportionality. So returning to our I equals 64 over d squared problem, I varies inversely as what quantity? So I varies inversely as the square of distance because it's inversely as d squared. So if I wrote that in words, I would say as the square of distance. So my whole sentence, if I was talking about the situation, I would say that I, or intensity, varies inversely as the square of distance, or as d squared. Okay, what is the constant of proportionality? All right, so the constant of proportionality, that is our k value, and it's 64 in this case right here. Then if d is doubled, what is the effect on I? Okay, so if I think about this, if I took, say, 64 over um, d squared, and I compared it with 64 over 2d squared. If I'm going to double d, it's going to turn to twice d, right? And so because that square is going to apply to the 2 as well as to the d, 2 squared is 4d squared. So if I double d, the result is that I get 1/4 of the original value. So the output is quartered, or multiplied by 1/4. Okay, the effect is 1/4. When we saw this in the direct variation, we would have said if we doubled in a k times d squared, the result was 4 times larger. Now it's divided by 4. It's 1 divided by 4, so it's 1/4 as large. Or we could say that here, just to say this again, the output is 1/4 as large. And again, I don't know why I said out. I meant to say output there. I just forgot to write put, apparently. Okay, so as we're mentioning down here, the procedure to find the constant proportionality is similar to the one that we used in the direct variation case. So let's take a look at the next situation, our last example here. This is still going to be about sound intensity. We're still going to be using I equals k over d squared for sound intensity, but the object is no longer going to be our iPod, so the intensity is no longer going to be 64. Now we're going to talk about the sound intensity made by a truck, and I have some information about the truck. If it's 20 meters away, then the intensity is 1,000 microwatts per square meter. So I can plug in the 20 for distance and the 1,000 for I intensity to solve for k. So I know the constant proportionality for this truck situation. So I've got 1,000 equals k divided by 20 squared. So that's the same thing as 1,000 equals k divided by 400. And then to solve for k, I should be able to multiply that 400 out of the denominator. So multiplying both sides by 400 gives us a k equals 400,000. 400 times 1,000 is 400,000. So in the case of this truck, my intensity formula is going to be 400,000 divided by d squared. Okay, so I can use this formula now to determine the intensity of the sound made when the truck is 100 meters away. Okay, so if we have our 400,000 divided by 100 squared, that gives us, let me type that in, 400,000 divided by 100 squared gives us 40 microwatts. Per square meter is the intensity measurement. So if it's 20 meters away, it's 1,000, but if it's 100 meters away, 40 microwatts per square meter would be its intensity. All right, and that's all.